Alright, I'm not feeling particularly well. I'll try delivering this lecture as far as I can. I haven't recovered yet from the fever and my sore throat, so we'll see how it goes. I wanted to go over the exam questions over here and also to start something new today, particularly about the AIDS detection topics. And also, if time permits, I wanted to go into OpenCV. Okay. So the first question was fairly straightforward. We got an input image and we have to convolute this with a given kernel. Part of the trick is that it has some negative entries, but I've actually written the conditions down that if you have these negative entries, thing is you have to multiply and then add, then divide. So the division part is going to be tricky because you have negative parts, -1 + 1, -2 + 2, and -1 + 1. If you add them up, that amounts to 0, which is definitely not going to work. So I said when you do the division, you have to consider the absolute value. Okay, so that's one thing. For the border pixels, let's say you're computing for this particular pixel, you'd have this surrounding parts which is not included within the image. In that case, I said that only take the part that only works over here, not the other ones. Okay. So let me show you how the calculation may work. I think I have it here. Yeah. Okay, so that's exactly the same question. I actually wrote this thing first and then took a snapshot and used that on the question. So how do we convolute this? I mean, for this pixel, this is not so difficult, right? We know exactly how to do it. So let us start with that then. And let me put the numbers first. So 5 over here. So from 2 to, if you take this, you're going to multiply it with 0. That's the idea. So this one gets multiplied with that. D4 into K4, yeah, that's right. Okay, so we got 112 over here. In some cases we can have negative numbers, in some cases we can have positive numbers. Thing is, we'd have to divide this by something, right? And that something over here is going to be what? 4 negative 4 over here and positive 4 over here. If you take the absolute value, that's going to be 8. Divide that by 8. So if you divide that by 8, we get Okay, let me look at it one at a time. B3, I3, C3, J3, K3, J3, B3, B4, I4, C4, J4.
So it should be 15.
B4. Yeah, this part. B5, C5. $15. Okay, let us take some time. I mean, maybe I did something wrong, but I just wanted to be sure. This is what we got, right? If you simply multiply the entries, 4 minus 1 is minus 4, 0 times 0 is 0, and here we got 5. So the sum of all these things is 7. So I guess this time I got it right. Okay? So 7 over here, and that thing is going to be divided by 8. We can't take fractional values. The exam question says that you'd have to round it. Okay.
Closest integer.
Yeah, to the closest integer.
So 1 represent
1. Right.
Okay.
So the easiest way to do that is to add 0.5 to it and then take the floor. So this is 0.87, right? Probably we got a round function as well. Let me see. Yeah. Okay, so we got a round, so that takes care of it. But otherwise it's the same thing. You add 0.5 and then take the floor. That will give you the same thing. Okay, so far so good. I mean, it behaves okay. We don't have any value that goes under 0. We don't have any value that went above 7. If it did, we had to cap it there. And that part is already defined as well. Okay. Okay, so now the tricky part, how to take care of the borders. Okay.
4 0 0 2 2 0 1 3.
Right, so over here, the thing is only this part would match. So we are going to multiply with that bit. Four times this plus 0 times 2 plus 2 times 0 plus So we got a 3 in here, and we have to divide it by how much?
2 plus 1, 3.
Divide by 3
Yeah. So then 1 to
and then round it up. We got 1 in here.
1.
So if you understood this part, see, this is the center and the center is over here, so we can only match this bit. So we superimpose that. We take and put it on top of it, carry out the multiplication, divide by the part that's common. So if we go to this bit, this part matches
Minus 2.
for 0.
For 0 is 6. 4 minus 1. Sorry, 4 minus 2.
4 into minus 2, 0 into 0, 5 into 2. Right? So that's what I was saying, that you take this part and you multiply it with the bordering pixel and divide by how much? 6?
Minus 2 to 6.
Yes, you divide by 6. Similarly, when you go over here, you take this part. When you go to the last one, you take this part. Okay. So not too complicated. Yes, it is probably time consuming, but
Sir, time consuming বড় কথা স্যার ভেজাল লাগে স্যার চোখের ইয়ে তো অনেক
I don't know. Well, to avoid that, the easiest solution is to write each and every number down, but that's going to take more time. Sort of what I did down here. I wrote down the multiplications, then I added them up just to make sure that the answer was correct.
মাসে সব যখন ক্যালকুলেশন করতে যাওয়া স্যার দেখা যাচ্ছে মাঝখানে
It's not supposed to be carried out by hand. This is a very silly problem to give in exam. It serves no purpose other than whether you can multiply and divide. Right? This is nothing related to image processing, but I wanted one question to be like that so that everyone can answer this thing. That was the whole point of it. If it were to me, I'd probably skip answering this question because we had other options.
Other options of theory which are more boring than this.
Okay. But is this thing clear? I mean, can we do this?
See, these answers are vary from person to person in this question.
For this one? No, not really. The correct answer is just one correct answer. Yeah, definitely you can answer something wrong. You can do the calculations wrong. If you're asking me whether I'm going to give partial mark, the answer is yes. So if your process is right, if you make some mistakes in calculation, that's okay. You probably lose some marks for it, but not the whole thing. But yeah, for this question, there is just one answer. So the answer cannot vary.
Sir, I saw videos of calculation in YouTube, but though they didn't calculate like these way. Those are really different. Like they take 6 times 6 matrix and then multiply it with 4 times 4 and then make a 5 times 5 matrix. That's really different things. How do that do?
I don't know which video you're talking about. Do you remember what it was?
Yeah.
Because we're talking about convolution over here, and the convolution matrix can be different. No one says that it has to be a 3 by 3 matrix. It can be a 5 by 5 matrix. But the process of convolution is the same everywhere.
Sir, these ones, a convolution of images by Alexandro Damlo. So you did the first video, It's about this one. And also the other videos, their calculation are also as same as this one.
So that's the convolution matrix, that's 3 by 3,
Yeah,
right?
exactly, sir. They have I think 6 by 6 and then it turned out to be something like 5 by 5.
1, 0, 1, 0.
Okay.
There's even on that DVD back, just so that it's up to focus. So basically, these are all the.
This is the 6 by 6 image, which is a grayscale image. In our case, that's the image, which is a 5 by 6 image. Okay, so the image can be of any dimension, any resolution. So that's the first thing.
But so their calculation is different. You know, they didn't do any divide things or something like that.
222, 225, where are they coming from?
256 ways.
We have
Well, the reason is their input kernel is just 1, 1, 1, and 1. So if you put it over here, you're going to add 222 with 225, 92, and 110. If you put this particular matrix just like that, if you look at the matrix over here, see there are 4 ones. So when you put it over here, only these 4 numbers need to be added. If you multiply it by 1, then it stays the same. So you add them up. And the reason we divide by 4, see, these are the 4 numbers they're adding up. It's actually nothing different. Maybe they didn't do the division part.
Yes, they didn't do that.
If you're talking about that thing, that part is for normalization, to keep it within the limits. If you add up all these numbers like they did, see that's 649. It goes beyond the range of 0 to 255. So you have to bring it down, and dividing by the summation of all the numbers in the kernel, that does exactly that. So it's actually a required step. I don't really have time to go through this whole video right now, but I'll do that at home. So I think they have some other angle for this. I mean, for other reason for not doing so, but this is a process. The division is a required process.
So finding the age value, I mean the key values.
Oh, how to deal with the border pixels?
Border pixels, yeah. So still
I know,
doesn't
well,
make sense to me.
For the border pixels, there are many different strategies that you can take. There is not one single strategy that works in all the cases. In some cases, you'd see that we leave it as black. Some cases, we'll leave it as white. In some cases, we'll just copy the values. But I just wanted to define it over here, and that's what I did in the...
So I didn't understand the calculation, the border, find out the border pixels. The first two or three.
Well, if you follow this, it says that you should use the part of the kernel that can be superimposed. So you take this kernel and you try to put it on top of this entire picture, and you'd see that not the entire thing is within the picture. So if you take this kernel and try to put it on top, you could only do it for this part. I think I can explain this a little bit better with some image processing tool. Like GIMP. Right, so this is the image, right? And let me take a copy of this. See, what we are trying to do here, in terms of convolution, we take this kernel and we put it on top of this image. That's called superimposing. Okay, so if I put it over here, you see how these things are multiplied. Okay, you take this kernel, the kernel was over here, and you try to put it on top of this. So if you're talking about this particular pixel, it's not a problem because it lines up nicely. But if you take it over here, some part of it is outside that image. So this is what is known as superimposing.
Can you take the upper values? Like minus
Yeah, we could take the upper values, but what do we multiply that with? There are no values there. So you could consider that those are zeros and leave them out. And right now, all you're left with is this bottom half. So that's how you put it over here. So 0 times 4, 2 times 0, 0 times 2, and 1 times 3. You add them up. Divide by how much? Divide by 3.
Yes, I really like this one.
And then for the next pixel, you go over here, the next pixel you go over here, and then you go over here. It keeps on sliding like that. Okay?
So for the like 2 1 values, I took like minus 2 0 1 0. Is it okay?
For what?
Like the
For which part?
for the 2 1 like 0 4 0.
For
the
2, 1, this one.
2 1.
2, 1 is over here. Row 2, column 1. You're talking about 1, 2.
Exactly.
Okay, so 1, 2. This one, alright. So if you try to line it up over here, the center pixel has to line up. Okay. Let me try to put some color over here so that you can track it better. Alright, so the red one is the kernel, and we have the grayscale one as the image. So what's happening over here when we take this part, you see that there is this center pixel, and let me use a different color over here. Maybe a darker shade. See, this is the center. This 2, 2 over here, this is right the center. So if you're talking about 2, 1, the center pixel has to be right on top of it. Then you carry out the multiplication. So minus 2 times 4, 0 times 0, 2 times 5, minus 1 times 2. That's how it goes. This is what we call superimposing, or put on top of. I mean, if you don't understand the word, then that's that. Okay, so for question number 2, I guess there is nothing really to discuss. It was given as a homework, and I expected that you guys did that at home. Yes, no, or... I mean, did you manage to answer this, or did you skip that?
No, yes.
Question
yes,
2?
yes.
Question 3, this is right from your textbook.
Yeah.
What's the answer?
The reason why if we add C, M and Y, then it turns out to be something near about great or. But we need a, that's why we need a different key. And another thing is like, we need to minimize the cost for the.
I'll take that as an answer. In theory, C, M, Y, if you add them together, it should give you black. Yeah. It doesn't, well, it doesn't turn out to be gray exactly, it turns out to be a muddy light color. So
Exactly.
it's brownish, it's not entirely black. So yeah, both the answers are correct, like what Shibli mentioned, that yes, we want to minimize the cost, and also since we don't get a pure black, we needed a separate channel. That's why we have it as C and Y and K. Alright, so this next one, what are the safe web colors?
216 colors. Like
We have
256
colors, yeah, right.
and
So
among them 40 colors are, they are not used basically, and 216 colors are used as safe, and they are used as just for the web colors. And easy to recognize by human. All theory stuff, like
Well, for the last part, I don't totally agree. It's more like they're easily reproducible. So the colors, how you represent that on monitor, how you represent that on projectors or any screen, they will vary, right? We don't have exactly the same color coming out for different devices. For web safe colors or safe web colors, the thing is they look pretty much the same regardless of what browser you use or what device you use. Now obviously if you turn down the contrast of your monitor or if you turn up the brightness of your monitor, things are going to be different. Or if you change the tone of your output device, things are going to be different. But in most cases, like these are safe, they're easily reproduced. So what they look like? Alright, so how do we generate the safe web colors? Or yeah, safe web colors, right? Safe web colors.
18 to 18 to 16.
How do you pick those 8? See, these colors, they are usually written in hexadecimal, right? We're talking about RGB. And for those of you who know a little bit of HTML, you see that we write them as hex codes, right? We write down 6 numbers. So for example, 3 to 1B and 2F. That can be some RGB code. Okay. Where B2 is the red component, 1B is the green, and 2F is the blue. Okay. What are our options for each for each hexadecimal digit?
Yeah, digit.
These are the options, right, for each hexadecimal digits, but not all of them are safe. So what we do over here, if you take the third entry for each of these are the safe digits. So out of all these things, how many did we get? 1, 2, 3, 4, 5, 6. Okay, so we got 6 of them. And if you combine them together, any of these 6, you're always going to end up with web safe colors. And the way you do that is you take 2 of these things, like so 3, 3, 9, 9. FF. So that's a safe web color. Again, you can create another one. You can say we take 0, 0, 9, 9. CC. That's also web safe.
All 0, all F.
That's also web safe. So if you go through your textbook or if you search for it on the internet, you'll find these patterns. Basically, instead of thinking about 6 different digits, you just think about 3 of them. So one from here, one from here, and one from here. Because the other one is just duplicated. Okay. So you can't have 3, 6, right? You have to have 3, 3 or 6, 6. It goes like that. And yeah, how many colors are there, the safe colors? You can look them up. I just wanted this concept to be there, and this is something that I didn't cover in class, but I wanted you guys to read the textbook, so it was just there. Okay. For the last question, this was pretty straightforward. I wanted you guys to calculate the intensity of the green color in R3G8B8 pixel. What does that mean?
Red 3, green 8, blue 5.
So we got 3 bits for red, 8 bits for green, and 5 bits for blue. So you're given a color in decimal number system 2, 1, 2, 4, 5. And all you need to do is to find out the green component from there. So can we do this? Three bits for red. Eight bits for what? Blue
Green,
and
sir.
right. Thank you. And that's for blue. So what we have now is 2, 1, 2, 4, 5. What do we do with it? We convert that into hexadecimal, or you convert that into binary, and then you take it from there. We know how to convert that into binary, right? So let me cheat a bit and bring up my calculator over here. 2, 1, 2, 4, 5. So it's written over here. We have 1, 0. How many ones? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so that's that. And it checks out. So from 0 to 15, we got 16 bits here. Out of them, 8 bits are for green, and remaining 8 bits are for red and blue. And this is what we are worried about. This is what we need to write. Okay? So green intensity is equal to 1001 0111. It's written in binary. That's the answer. If you leave it like that, then that's fine. If you thank you. If you wrote it in terms of decimal, that's also fine. Okay. Okay, so for part B, we have a Windows BMP image, and I wanted to know, where do we start writing pixel data? What row and column gets written in the very first pixel. We got C columns and rows. Y10. In Windows BMP, where do we start writing the pixel data? There's a very specific answer to that. 1, 1 to 2. And how did you come up with that answer? Now the answer is right, but we've been looking at this thing, this Windows bitmap format, right? And here what we know is that we have a fixed number of bits for the header part. It's written somewhere.
So we use it enough.
Let me open this up. I think it's easier done that way. Okay. So here's the thing. We have this signature and other stuff. This takes about, I guess, 40 bits, and over here we have another 14 or 16 bits, and down here we have a color table, and this is where the pixel array starts. Okay. So we have calculated the offset when we wrote our code, and it checks out, like that's what it was. 122 was 122 or 112, either of that was where we started writing this thing from. And this is actually written in one of these places. What's that? Yeah, that number 122 was written in 10 to 14, and this thing is actually written somewhere in these tables. So this is question. The target of this question was to help out students who wrote the program or part of it. They would know that. Yeah, it's written there. So the value that's written over here gives you the pixel address. And we calculated that in our code, and we printed that out as well. So that's the answer I was looking for. From which address we start writing the pixel. So that's one thing. And the next part of the question was, imagine that you have an image with C columns and R rows. What would be the very first pixel, the row and column index, when you write it down? Let me leave this thing in front of you and help me out. Yeah, the very first one. What would be the row index and column index? No, it's not 0.
0 is -1.
Is that?
0 is -1 is like this.
H stands for height, right? That's the number of rows. So 0 r minus 1 is the answer. When you write down the pixel data, you don't write pixel 0, 0 in the starting index. Pixel 0, 0 is down here. Okay, so the image is actually flipped over when you write this thing. This is how it is. Alright, so any question about any of the exam questions or anything for that matter? Okay, tell you what, I want to continue, but I need a break. Terrible headache, so maybe like 20 minutes. We will start talking about age detection after we get back. So let me just pause this thing over here.